In quantum mechanics, for a single wave, there is a time dependence in its mathematical expressions, but still the wave is not time dependent. That means it's a stationary state, and the reason is that the time dependence cancels in physical predictions, and so the time dependence is not measurable or not visible. So that is the first thing I have to say in that. And then I have to generalize it that the same result is valid for any wave, namely any wave packet, if potential energy is time independent. So the same thing applies, and there is a calculation for that, and in calculation we get time dependence and also what is called time independent Schrodinger equation. So that is the full plan, and now I say that in detail of the first claim, namely that there is a time dependence in the mathematical expression for a plane wave. Now I have introduced a factor which is called small psi, and the full time dependence is capital psi. So the expression for a plane wave is e power iota k dot r. This iota k dot r has been named as small psi, and the time dependence has been separated out, and this moment is pinpointed in that here you see only explicitly written time dependence. Now that is just a way of writing a plane wave, nothing new. And now, is this time dependence physical or not? That's the question. And to get the answer, you see physical predictions. And in physical prediction, you have, for example, probability density. The probability density is obtained by multiplying wave with its complex conjugate. So that means this time dependence is also multiplied with this complex conjugate, and this positive and negative powers in exponent cancels out to give 0, and the result is e power 0, namely 1. So this time dependence cancels, and the result is time independent, and hence the plane wave, which I just wrote in a form, the plane wave is time independent or wave, or is a stationary state. So that is for a plane wave. Now the next topic is it only for a plane wave? And the net answer of this, the purpose of this lecture is to tell you that it's not only for a plane wave. It is for any wave, and the reason is that any wave satisfies time independent time dependent Schrodinger equation. So the time dependent Schrodinger equation has time derivative, and that's why it's a partial differential equation. So we do the mathematical step of converting this partial differential equation to ordinary differential equation. You can say that we are doing it for the mathematical step forward, in that partial differential equations are very difficult to solve, and when we convert that to ordinary differential equations, it becomes easier to solve. So you do that mathematical step, and all the claims which I mentioned, others, they are, this means about time dependence and about time independent Schrodinger equation, they are obtained in the mathematical process of converting partial differential equation to ordinary differential equation. Now if you take that as a mathematical aim, then the question is, what is the technique available for converting a partial differential equation to ordinary differential equation? And the quite common answer is, quite frequently used technique is what is called separation of variable. Separation of variables says that you can write the dependence on two variables as a product of dependence on one variable and multiply with a function of other variable. So this dependence is factorized out. So this means the variables are separated. Now that's good if you can separate variable. You can see that has mathematical advantages etc. But the question is, can we do that? And the answer is, there is a theorem type. If you want me, I can prove that if your differential equation has additive separateness, that means it is additively separable. One term depends upon, the crucial word is the term. Terms add. So the one term depends upon one variable, or maybe another term also depends upon one variable, and so on. And then the dependence on the other variable has a separate term, separable. So if differential equation is separable additively, then your result can be written as a multiplicatively separable. So before showing the steps, I have to discuss if this time dependent Schrodinger equation, because you see time dependence, is additively separable. So that's the question, and to get the answer, you see here it's only time dependence, so it's a separate. Here it's only del square has the second x derivative plus second y derivative plus second z derivative. X, y, z are all positions, so that is a function of position only. Only position here, only time here, that's a separable. But here is a mix. So that means we can use technique only if this mixture is finished. That means only if v is a function of r only. So if v is a function of r only, you get separable terms. There only time, here only position, here with that only position. Okay, so position separated, time separated. Now the mathematical theorem says that in that case your solution is also separated, is factorized. That means if the equation is additively separable, that means has a term, your solution is multiplicatively separable, that has a factor. So that's a factorized separation, is particularly in form of factorization. So that is the claim that this technique can be used, and the claim is implemented in the next slide. The next slide, the first line is nothing new. It's already appeared in the previous slide, that if potential energy is a function of position only, this factorization claim is not new. That was also in previous slide. And not independent. This is time dependent Schrodinger equation. That is also not new. And new things start when you start putting things. In capital psi, you write that. Now what happens? What kind of differentiation? So you see, when you put here this time derivative applies only on this capital T factor. So this is the derivative, and it's only time dependence is differentiated, and here the differentiation is only with respect to one variable. So you see, partial differentiation is converted to ordinary differentiation. So that's a step towards converting partial differential equation to ordinary differential equation. Okay, you can say it's only one step. I have to tell further mathematical details as well, and then details are that is for differentiation, and that psi, which is position dependence, comes out of time differentiation. That's the left hand side, and right hand side, you remember I have saved space and I've written only h, but h has appeared many times. So you think you start remembering it. H has del square. This is position dependence. and then V, and we are taking a case and V is also has position dependence. So H has only position dependence, that operates only on position function, and the time factor comes out. So now you may say that why I have done it. To see the advantage, what you do is you divide both sides with this product. So left hand side, what happens is that this psi gets cancelled with psi, and you have 1 over t only, and then other things as remain. That's the left hand side. And right hand side, capital T is cancelled, and you have h psi divided by this psi. Now you have situation is that left hand side is a function of one variable, and right hand side is a function of another variable, the second variable, namely position. So what logic says for that kind of situation, and what logic says is that left hand side depends upon only one variable, namely time here. So it means if there's a crucial word is the word if. You have to pay very much attention to this if. If it depends upon time, it has to be also equal to right hand side which does not depend upon time. So if it depends upon time, it is equal to something which is independent of time. It is equal to something which does not depend upon time. I repeat, if it depends upon time, it is equal to something which does not depend upon time. So what is the way out of that? In the way out is that if condition is not satisfied with if it depends upon time, you are in trouble. So that means it does not depend upon time. So that means it's a constant, and if left hand side is a constant, right hand side is also a constant. And as far as units of this constant, they are easy to see from right hand side. Psi units cancel, and H Hamiltonian as units of energy. So it's a constant energy. So we have two equations, left hand side equal to constant energy and right hand side equal to constant energy. So maybe I start with right hand side. So right hand side constant equal to energy. I mean, I started with right hand side because that is simpler to tell you answer. Here the calculation are lesser. Just all you have to do is just use small psi, you multiply both sides. So from left hand side it disappears and it appears on the right hand side. So that you remember in H you have derivatives. So this is the differential equation, and that is called time independent Schrodinger equation. So that is from right hand side. And from the left hand side you do mathematics. That is equal to E. You take a small dt on the other side and you integrate, and you make indefinite integral. This dt over t, the indefinite integral give you log natural, and here dt becomes the antiderivative as t, and then you have a constant of integration. And now we want to do t, time dependence. So we have to finish log, and to finish log we have to take anti-log, which is in this because it's a natural log. So anti-log is e power. So what happens is here you get log and anti-log cancel, you have a t, and here you have anti-log which is exponential, and the constant appears as another exponential of constant is the constant. These are different constants, you remember. So that's the mathematics. What is the physics lesson out of it? And for that you note it that this this is if it looks new to you, pay attention to that. E is equal to h bar omega, and h bar cancel, then you have e power minus iota omega t. Do you recognize what? No, that is the time dependence. We started the lecture about it. There was time dependence of plane wave, and I said many things about that time dependence. That means it cancels in physical predictions and time independence and so on. So that was for a plane wave, and now I shown that this is not only for a plane wave, that is for any wave if potential energy is time independent. So that's the conclusion of that, and that I write 2 lines of conclusions, 3 lines on this slide, and there with this slide I finish. So I just write it what I promised, and that is all is a summary of all which appears in front of you in this slide. That means if potential energy is time independent, Then time dependence is same as that of a plane wave. So all the comments apply. Stationary state is also stationary state. And stationary means there is no time dependence, there is position dependence, and position dependence is given by, you remember, you have to remember name, given by this is called time independent Schrodinger equation. So that's all in this lecture. Thank you for watching, and do not forget to subscribe to this channel.